Many people think that training LoRa is an exclusive domain for tech experts, with high difficulty and entry barriers. But in reality, don't be intimidated. Give it a try, and you'll find that it's not much more complex than generating images or videos. Nowadays, even consumer-grade GPUs can handle it, and there are even some brute force methods, such as aggressively selecting images or skipping parameter tuning, that can still produce a decent LoRa. This Chinese New Year, I went back to my hometown. How could I let my computer sit idle? Taking advantage of this opportunity, I gathered a bunch of reference images based on my understanding of LoRa training and ran it non-stop day and night. By the end of the holiday, I had gained quite a bit of experience, so I decided to turn it into a video to share with everyone. First, let me put a disclaimer out there. The Black Forest Lab hasn't released any official guidelines for training Flux LoRa yet. So everyone, including myself, is figuring things out based on prior experience with training Stable Diffusion, SD. Moreover, training on a 4080 takes significantly longer than generating a single image, so for now, I can't do highly detailed parameter comparisons and adjustments. That means the methods and parameters I'm sharing today may not be the most optimal, but I hope they can help demystify LoRa training and provide an easy-to-follow guide for beginners. Once I manage to get my hands on a 5090, which is really hard to buy, I'll definitely continue experimenting and updating. Now, what exactly is LoRa? LoRa, short for low-rank adaptation of large language models, is a technique that allows us to fine-tune large models efficiently with fewer resources. The core concept is low-rank decomposition, which expresses the parameter update matrix delta W as the product of two smaller matrices A and B. During training, only A and B need to be updated, eliminating the need to store and manipulate the full W matrix. This greatly reduces VRAM usage and computational costs. Using a trained LoRa is like giving a large model a crash course. It can learn to recognize a new character, such as Nezha, and accurately reproduce his design in different scenes. It can master drawing a specific dress, ensuring consistency in details from the front, back, or side. It can even design entirely new products that remain consistent with a brand's established style, yet differ from anything the brand has released before. This is exactly why there are countless reasons to consider creating a custom LoRa. If you can't find the right model online, why not take the leap and train one yourself? As for how to train LoRa, let me share an analogy about baking a cake. This perspective comes from an article published on Civitai on July 11, 2024, by Nexo, with a straightforward title, Creating LoRa is like baking a cake. The entire LoRa creation process is divided into three parts. Collecting and processing the dataset corresponds to preparing ingredients. Setting training parameters, such as rank and learning rate, is like experimenting with different baking recipes. The training process itself is similar to patiently waiting for the cake to bake. Among these, the first part, collecting and processing the dataset, accounts for 90% of the challenge. A high-quality dataset can yield great results even with default parameters. To put it in simpler terms, when you have premium ingredients, even the simplest cooking method can produce excellent results. The next two parts involve choosing the right training tools, and having enough VRAM, and setting appropriate parameters. Currently, there are many tools available for training LoRa on the Flux model. Several websites and cloud service providers offer online training services. And some independent developers, such as Aki, have released integrated Alchemy toolkits. Even if you're only using Comfy UI, you can train LoRa by installing plugins like Comfy UI Flux Trainer. That said, most of these tools are actually built upon Koha ISS's open-source SD scripts, optimizing and repackaging them. The core parameter logic remains largely the same, the main difference is just where you input the parameters. Additionally, most tools support saving training configurations as TOML files, making it easy to load and reuse settings across different tools. Today, I'll demonstrate different LoRa training approaches based on three distinct needs: Demon Child Nezha, character modeling; a specific brand's plush toy, style replication; a dress, emphasizing fine details. For training tools, I'll showcase two options. 1. A local Comfy UI setup with the Flux Trainer plugin installed. This leverages the familiar Comfy UI system but requires a powerful local GPU. 2. A cloud-based trainer. This eliminates the need for manual setup but may come with usage limits or costs. You can choose the method that best suits your needs. Let's first talk about the difficulty levels of the 3 LoRAs we'll be working with today. Character LoRA is the easiest. Since it only needs to focus on appearance features, such as face shape, hairstyle, and skin tone, the model, Flux, already handles this well. Even if there are slight variations in the final images, users tend to be very tolerant of these differences. Style LoRA is of medium difficulty. The model must extract common features like line work, texture, or atmosphere from different images. This demands a higher level of abstract understanding and might require longer training time. However, since style is inherently subjective, as long as the result is close enough, users usually accept it, even considering it to match the style perfectly. Specific clothing LoRA is the most difficult. In addition to reproducing complex patterns, materials, and intricate details, it must also handle multi-angle adaptation and dynamic deformation, ensuring natural interaction with the character's movements. If these details are not properly handled, the inconsistencies become immediately noticeable, breaking immersion for the viewer. Let's start with Nezha. Since character LoRA is the easiest, I'll introduce a quick and effective brute force method that delivers solid results with high cost effectiveness, making it perfect for beginners. Step 1. Collecting and selecting images. This movie has been hugely popular recently, so it's easy to find a large number of high-quality images from public networks. To keep this beginner-friendly, we don't need a highly diverse dataset. Simply picking around 10 clear images where the character is fully visible is enough. However, it's crucial to avoid incomplete character images. Since this plan doesn't involve captioning, the model won't understand this is half of Nezha or this is Nezha's fire wheels. So let's not make things unnecessarily difficult for it. Of course, if you want better results, you can collect a more diverse training set, including different poses, expressions, angles, backgrounds, and lighting conditions. This helps the model learn a more comprehensive representation of the character, making the final outputs more versatile. However, this approach requires more training steps and time, and if the dataset is too large, manual fine-tuning of training parameters may be needed for proper convergence, making it more suitable for experienced users looking to refine their results. For this guide, we'll keep things simple and stick with 10 selected images. Step 2. Cropping images. Some images might include other characters, for example, this one features both Nezha and Tai Jinren. In such cases, we need to crop out unrelated parts. Another issue is aspect ratio. While enabling multi-aspect ratio buckets can handle various resolutions, having too many buckets can significantly slow down training. Therefore, I prefer to pre-crop images beforehand, keeping aspect ratios limited to just a few fixed formats. For example, converting a messy collection of images into square images and one fixed horizontal/vertical aspect ratio. As for cropping tools, a completely free online website like Brime is a great option. It allows batch cropping and resizing efficiently with an easy-to-use interface. Of course, you can also use Photoshop, Windows Paint, or any other drawing tool you're comfortable with. Once everything is done, we replace the original images with the cropped versions, and that completes our Nezha dataset. I have some preferences when it comes to folder organization, so I use a few nodes from my own plugin, Comfy UI Nodes, to tidy things up. I usually do just 2 things. 1. Use the Batch Convert Image Files node to standardize all images to JPG or PNG format. 2. Use the Batch Rename Files node to rename files with a numeric prefix for consistency. Since the images in this dataset are already in JPG format, I only need to rename them. I disable the Convert node, copy the Nezha dataset folder path into the Batch Rename Files node. Hit Run. And in an instant, the renaming is done. Next step, captioning. Now, it's time to add descriptions to each image in the training set. This helps the model precisely bind the learned features to the correct trigger words during training. Based on my understanding, Flux captioning methods can be categorized into 4 main approaches. 1. Subtraction method, defining by exclusion. This method labels all features that are not part of the trigger word. It isolates the target content, such as a specific character, style, or action, from the background and noise, ensuring the model focuses only on the parts uniquely explained by the trigger word. This approach dates back to the SD 1.5 era and remains a classic, preferred method, especially for clear target, simple background cases. 2. Semantic replacement. Here, we create a detailed description of the image and replace the target content with the trigger word. This directly binds the trigger word to the target in semantic terms, allowing the model to anchor the feature precisely. This method places a stronger emphasis on how the target integrates with its context rather than isolating it. 3. Core feature binding. This method extracts the essential characteristics of the target and constructs customized keyword phrases as trigger words. It creates clear semantic boundaries and provides richer input information, helping the model converge more efficiently, especially useful for tasks requiring complex semantic representation. 4. Minimalist approach, letting it learn naturally. This method keeps things as simple as possible. Each image is assigned just one trigger word, with no additional background or detail labeling. It relies on Flux's strong abstraction and generalization capabilities to automatically identify shared features and link them to the trigger word. This drastically simplifies the tagging process, making it efficient and surprisingly effective, particularly for character learning. However, this approach can lead to feature bleeding, potentially contaminating broader concepts in the model. But in most cases, this isn't a problem, since the goal of training a LoRA is usually to generate that specific character, and conflicts only arise when training multiple characters simultaneously. From my experience, these 4 approaches each have their strengths in different scenarios. For character training, the minimalist approach is simple, efficient, and stable. For complex details, such as an intricately designed dress, core feature binding helps the model converge more precisely. For style training, I prefer a hybrid approach, using core feature triggers while also tagging main subjects to reduce noise, improving generalization ability. Since Nezha is a straightforward character training case, we'll go with the minimalist approach. First, we need to choose a trigger word. Ideally, we should create a completely new word that Flux doesn't recognize. This prevents the model from linking it to existing semantics, making the training process faster. How do we check if a model already knows a word? It's simple, generate a few images using Flux based on that word. If the results are completely random, with no obvious similarities, then it's a perfect trigger word. I chose Nezha. Flux has no recognition of it. Embedding the trigger word in captions. Most training frameworks require explicit caption files, and they will throw an error if the file is missing. So how do we ensure our trigger word is properly written into the caption files? My own plugin, Nezha, has a node specifically for this. Add batch sync image caption files in Comfy UI. Enter the folder path. In the content field, input the trigger word. Add another node to check logs. Click Run. This will create a TXT file with the same name as each image. And we're done. Fine-tuning image descriptions. If you want more detailed captions, you can use a visual language model for auto-labeling. If you're using my Comfy UI Caption This plugin, besides Florence 2, you can also try DeepSeek's Janus Pro for descriptions. Regardless of which tool you use, follow these key guidelines. Caption file names must match their corresponding images. The extension depends on the setup, usually .txt or .caption, and they must be in the same directory. If using a trigger word, place it at the very beginning of each caption file. Keep descriptions concise to prevent the model from struggling to process them. Manually check the results to avoid contradictory descriptions. This is especially important when dealing with characters like Nezha. The model might misinterpret different images in the dataset, sometimes seeing Nezha as a cartoon character, sometimes as a girl, a boy, or even an anthropomorphized animal. If we train directly without intervention, the model may suffer from underfitting, producing poor quality generations and wasting effort. That's why, for LoRA character training, I personally prefer not to add captions at all. Dataset ready. Time to bake. Now that our ingredients are in place, let's start baking. If you have a powerful local GPU, at least 16 GB VRAM recommended, you can train using the Flux Trainer plugin by Kajai in Comfy UI. I prepared a workflow for this, which is fairly extensive. We'll go through it step by step. Today, we'll focus on the overall process and key modifications. In the future, I'll make a separate video discussing how to fine-tune parameters in detail. The left side nodes handle loading the dataset. Train dataset general config can be ignored for now. In train dataset add, the width and height define the resolution to which images will be resized during training. The resizing is based on total pixel count. Other example, if the dataset contains 1024 by 1024 and 1536 by 1024 images, they will be scaled to 512 by 512 and 640 by 384, respectively. If you want LoRa to learn more details, you need to increase the size, such as 1024 by 1024, but this can put a strain on the GPU. Batch_size refers to the number of images processed per training step. Increasing this value helps with model generalization but also requires more VRAM. The first text box is for entering the training dataset path. The second text box is for entering the trigger word. If you have prepared caption files, it is best to leave this blank, otherwise, the specified trigger word will be automatically added at the beginning of each caption. As mentioned earlier in dataset preparation, the training script will automatically process images to the appropriate size based on these parameters. Keeping everything at default is fine. Number_repeats is an important parameter that determines how many times the entire dataset is repeated within a single training epoch. The total training steps are calculated as number of images times number_repeats, divided by batch_size times epoch. For example, in this training session, I have 10 images, repeated 50 times, with a batch size of 1 across 4 epochs, resulting in 2000 steps. Some of you might wonder, if I set number_repeats to 10 and increase the epochs to 20, I still get 2000 steps, would that work? My understanding is, higher repeats help learn specific features but can lead to overfitting. Higher epochs improve generalization but increase the risk of underfitting. You need to set this based on your training goals. Experienced users should reasonably save training states, save_state, and adjust repeat values dynamically based on the model's current performance. There are also 2 disabled nodes, which also add datasets and serve 2 main purposes. 1. Multi-scale training. Learning the same image at different resolutions to improve the model's ability to handle various resolutions. 2. Sample weight control. Assigning different repeat rates to different types of images. Increasing the weight of key samples, such as highly detailed images, in training. This time, we are keeping things simple, so we won't use them and will leave them disabled. The middle node is used to set training-related parameters. In the Flux Train Model Select node, choose the local Flux base model, VAE, and clip. I am using an RTX 4080, and both the model and T5_XXL are set to FP8. The parameters in Flux Train validation settings are used for generating images during model validation. The default settings are fine, but since training already puts significant pressure on VRAM, the image size can be reduced. The Optimizer config node configures optimizer behavior during training, including learning rate adjustment strategies and gradient clipping. There is no universal best configuration, each has its own strengths and weaknesses. For experienced users, use Prodigy in the early training phase for fast convergence. Then switch to AtomW to improve accuracy and achieve the best results. For beginners, keeping the default parameters, AtomW 8-bit and constant, is the most suitable and stable choice. The model output configuration involves 2 nodes, where we define the model save path and name. I created a corresponding folder and named the model LoRa_X. Next is the prompt node, which is mainly used in combination with the sampling parameter node to generate images. The prompts are separated using a vertical bar. I have set up 4 groups, which are used to test the standalone trigger word and combinations with different elements, such as clothing. In the init Flux LoRa training node, there are numerous parameters, don't panic. Let's focus on the key ones. Network_dim is the rank of LoRa, typically ranging from 4 to 128. A higher network_dim uses more VRAM and improves detail capture. However, with insufficient data, it may overfit. Theoretically, it enhances capability, but practically, it increases VRAM usage. Choose based on your hardware. Network_alpha is best kept at the default value of 1. Previously, this value was typically equal to dim, but Flux handles it differently. Learning rate, recommended starting value, 4 times 10 to the power of -4, a common initial setting. If dim is large, you may increase it accordingly. There's no universal optimal value, adjust it based on training progress. Training steps, only usual initial setup is 2000 steps. If time is limited, you can start with 1000 steps and resume later by loading the saved training state. For now, you can ignore the other parameters. On the right side, these 4 modules serve as checkpoints to save the LoRa model and display training progress. I set it to save every 500 steps, which means 1 checkpoint per epoch, 10 by 50. I'll soon show the training curve. Whether to enable save_state depends on your needs. I usually keep the last 2 checkpoints. If training fails, e.g. gradient vanishes/explodes, loss becomes nan. You can load an earlier checkpoint, tweak parameters, and retry, no need to restart from scratch. If training steps are insufficient, you can continue from a checkpoint instead of retraining, saving time. At the end, there's a summary section that consolidates all LoRa-generated images across different training stages for easy comparison. Now, let's hit run. The LoRa training, baking, begins. The terminal indicates it will take about an hour. I sped it up, and after 17 minutes, the first epoch of LoRa was completed. However, image generation took longer. Since the output resolution was too large, sampling filled up VRAM. With screen recording turned off, training finally finished in 2 hours. For now, I'll set aside this LoRa model, and we'll discuss testing later. Let's push forward and finish the training explanation in one go. By the way, this method works fine for real people too, but use images from the same time period for consistency. And of course, avoid copyright infringement. Training a style LoRa. Unlike character LoRa, training a style LoRa is more complex. To demonstrate how to train a LoRa for a specific brand's unique style, I collected 217 product images from an e-commerce website. All images were square, making processing much easier. Step 1. Preparing the captions. Select 6 images and put them into a new folder. In Comfy UI, use the Florence 2 caption images under directory node from Comfy UI. Caption this to generate captions. Use the summary text files node to compile them. Finally, connect to show anything and run the process. Now, we can reverse engineer the complete 6 prompt phrases from the node output. Step 2. Extracting core features. Open a chat window with a large language model. Input the captions and ask it to summarize the core features, quick and easy. Step 3. Assigning captions to the dataset. Back in Comfy UI, add a batch sync image caption files node. This automatically generates a caption file for each image in the dataset, embedding its core features. Click Run. The caption files are instantly added. I also removed some duplicate images, leaving a total of 149 images. Step 4. Fine-tuning captions. This part requires manual adjustments. To avoid interference from the image subject, each caption file must explicitly mention the subject. Example, for a cake image, add a cake to the caption file.
A few moments later.
After some time, the dataset is fully prepared. I trained this LoRa using a cloud platform trainer. After entering the name and trigger words, I created a folder to save the model. Then another one to upload the training dataset. I checked a few captions, everything looks good. Since there are a lot of images, I chose to repeat them only 4 times, running 4 epochs for better generalization. That's a total of 2,384 steps. Because the original images weren't very large, I set the resolution to 512 by 512. If you have higher quality data, you can train at 1024 by 1024 for better results. I kept the learning rate at 4 times 10 to the power of -4, which I prefer as a starting point. Since there are only 4 epochs, I saved the model at the end of each one, with a dimension of 32. Sampling was done every 500 steps to check the results, using the long trigger phrase plus a frog. Once training started, we skipped the process and went straight to the results. Looking at the sampled images, they clearly show the distinct style of the brand. I downloaded the model as well, we'll test it later along with the others. Now, let's talk about the final type of LoRa in today's video, one for a specific piece of clothing. Compared to CAT-VTON, this method is more reliable and can handle non-frontal views that CAT-VTON struggles with. Generally, I select 4 to 6 images of the clothing item, including front, side, and back views. It's even better if there are model or mannequin photos. For annotation, first, I summarize the key features using the same method as before. Then, I add the reverse-engineered prompt of the image. However, it's best to double-check, especially for clothing where the front and back might be hard to distinguish, requiring manual corrections. Here's how I usually set the parameters: a higher dim, such as 32 or 64. A lower repeat count, relying on more epochs for learning. I've tested this method on multiple outfits, and the results are consistently stable. That concludes the training section. Now, let's discuss how to evaluate a LoRa. I once read an article that defined a scoring system based on 4 key dimensions: 1 core performance, accuracy plus generation consistency, 2 side effect control, 3 fundamental quality, correct anatomy, structural accuracy, 4 documentation and usability. It used a weighted algorithm to generate a star rating. However, I have a slightly different perspective. I believe evaluation criteria should be adjusted based on the specific use case. For example, when precisely replicating a piece of clothing, slight beneficial overfitting can enhance detail retention. When training a LoRa for personal portraits, bleeding, a common side effect, doesn't interfere with other model terms, so it's not necessarily a flaw. When creating a LoRa for mythical characters, having extra arms or heads is common, so anatomical deviations shouldn't be penalized. Taking today's LoRa examples. For accuracy, the Nezha model just needs to resemble the character. The style LoRa must align with the brand's distinct style. The clothing LoRa requires precise details. For versatility, the Nezha LoRa was trained with a straightforward method, so my expectations are lower. It just needs to allow outfit and scene changes. The style LoRa should adapt to different subjects, even ones outside the training set. The clothing LoRa should be wearable on different models and allow multiple viewing angles. I don't consider bleeding a major concern here. Except for the character LoRa, Nezha, the other models have no significant issues in this regard. At this point, the video is already quite long. I know many of you still have questions about LoRa training, and I have plenty more insights to share, including the logic or magic behind parameter choices. How to use multiple datasets to enhance results. How to analyze charts and sampling results to fine-tune datasets and parameters, fixing issues like non-convergence or broken models. Layered training, training only certain blocks to significantly improve speed and reduce model size. Using masks to exclude unwanted parts of training images. There's a lot more, but we'll save those for another time. I also hope you'll share your experiences and techniques. Since there's no official guidebook for this, we're all explorers and learners. I'd love for us to grow together. That's it for today's video. See you next time.